I will stand up in a second to do a brief introduction, or you can, whatever you prefer. I'm going to link this out on social media.
Like a game within a game. The game is to figure out the rules.
It's just because you might be also interested in card game Flux.
Oh, yes.
Flux. It starts out with only 2 roles.
Okay.
It's like if I'm on cards, play 1 card. But then what happens is you can play cards that actually change the rules. That add rules like pick up 5, play 5. That change the rule. So if you have these 5 cards in front of you, you win the game. But then I can play another goal on top of that.
5 different goals, 5 different parts that win.
So I can flip out what the winning condition is.
The game actually starts with no goals at all, so that's you can't win at the beginning.
Yeah.
This sounds very interesting.
All right. So it seems we lost a number of people to lunch. I suspect that they will come back in slowly, hopefully, ideally. But we're going to go ahead and start back up. The next speaker we have is Srijan, who is a Stanford postdoc. And I'm very excited about this talk as it sort of introduces a sort of type of knowledge extraction that we haven't yet even touched on in our workshop, but I think is a very important and promising one for future research. All right, thank you very much.
Yeah, thanks for inviting me. This is super exciting, and I was following this workshop like last year as well, so it's really great to be a part of it. So today I'll be talking about network extraction to study face-to-face deception. And this is joint work with a lot of people, and most of the work has been done by Chongyang, who is a PhD student at Dartmouth College, and other people at part of this work are Julian Leskovic at Stanford, Miriam Netzer at UC Santa Barbara, Jen Enamaker at University of Arizona, and V.S. Subramanian at Dartmouth College. So let's get started. So we lie in everyday interactions with with people around us, in online interactions, in face-to-face interactions, and so on. And deception in online interactions and in face-to-face interactions is of high impact, both because it leads to high-stakes situations, such as in law enforcement, intelligence gathering, and in financial fraud. And understanding and detecting deception is really crucial because it can lead to a lot of financial fraud and security problems. And games have been a very, very vital component of understanding and studying deception because it provides an observable environment and a controlled environment by the designers to study, extract, and predict deception. And there have been a lot of studies that involve games and deception, but have particularly been focused on online communication and have focused on studying language, social media analytics from these interactions, and even studying the conversations or extracting networks from these interactions. But most of this work has been focused on online communication instead of face-to-face interactions. What I am interested in is studying deception in face-to-face interactions and communication. And this is super important because high-stakes decisions are actually made in such situations rather than in online conversations. And deception in face-to-face communication, discussion, or interactions is highly undesirable. The main question of my research is how can we, as researchers, identify who is being deceptive in face-to-face multi-party discussion. So a lot of research has already been done in face-to-face deception. But so let's take a look at what has been done. So there's a lot of speech analysis, which has particularly been focused on games. So they look at the intonation of speech, the frequency of words that are being spoken, or like how fast is a speaker speaking, and so on. So that's primarily based on speech. There's a lot of facial analysis. So they put a camera, they put essentially record people's faces, and then they would try to predict from micro expressions or from their interactions with other people how whether a person is being deceptive or not. There's a lot of work also in courtroom trials. So these are essentially videos of people like defendants from actual court cases, and they're trying to predict where essentially these people are lying and where they're not. And then there's a lot of work on studying bias while in these interactions, and also cross-cultural deception. But a lot of this research is limited by publicly available ground truth data. And the second problem, or the second challenge here, is how individual analysis of people, like a lot of work that has been done on understanding whether people are lying or not, is done from video analysis. So like facial structure, facial expressions and facial structure and so on. So what this does is it ignores person-to-person interaction. So if there are multiple people in the room and I'm speaking and and I'm lying, individual person's video analysis would essentially ignore person-to-person interaction. So this would kind of ignore the fact that I am, let's say, smiling at someone, or I am shouting at someone, and so on. So the key here is, how do we actually study interpersonal interactions, or how do we study how two people are interacting with each other? So coming from a network science group and a data mining group, I use the language of networks to do this. So to solve the first problem, we essentially need to collect data sets which have ground truth of deception. And to solve the second problem, we need methods that can extract networks from videos. So the pipeline of my deception research essentially comprises of 3 steps. The first is collecting data sets that have ground truth, so which we then use to extract networks of interactions from these data sets. And the third is, finally, from these networks, we then try to predict and reason about deception from these networks. So today I'll be talking about the first 2 steps. I'll be talking very briefly about the first one, and mostly focusing on how we can actually extract networks of interactions from multi-person videos. So let's start with how we actually collect this data. So the game that we use to elicit deception is called resistance. I see some nodding heads and some smiles, so I assume some of you know it, but let me briefly explain what resistance is. So each game essentially has 5 to 8 players, in which there are 2 to 3 spies. Now the spies know who the other spies are, but the non-spies do not know who the other, they only know their own identity, that they are non-spies, but they don't know who the other people are. And the task of the non-spies is primarily to identify who the spies are. The game itself is divided into multiple rounds. Each round, one person is selected to be the leader, and each leader selects two other people to go and secretly vote. Now, each vote can be either positive or negative. If a negative vote is, if at least one negative vote comes from the 3 people who are voting, then spies get a point. And if all 3 vote positively, then the non-spies get a point. At the end of 5 rounds, the team that has most number of points wins. So seems complex, but think of it as every round 3 people vote. If in each of these voting sets there's all positive, then non-spies get a point. If there's at least one negative, then spies get a point. At the end of 5 rounds, the team with the most points wins. The dominant strategy here for the spy is to always try to be deceptive, or is to pretend that they are non-spies. So by design of this game, we have spies who are always being deceptive and non-spies who are not being deceptive. By the way, feel free to interrupt at any time, ask questions. It's supposed to be very, very interactive. Okay, so this is the game setting that we are using, and there are lots of different games that are similar to this. You may be aware of Mafia or Werewolf, or there might be others as well. So we picked this game because it's more structured in the sense it has 5 rounds and so on and so forth, and nobody gets eliminated. So for example, in Mafia, people get eliminated at every round. We didn't want eliminations. We wanted the group of people to stay the same. And it's a small group. It's 5 to 8 players per game. But what we do after that is we actually go around the world. This was in collaboration with social scientists and communication scientists from Santa Barbara and University of Arizona. And they went around the world to lots of different universities and paid graduate students essentially to play this game. They essentially have recorded 27 games that are each of about an hour, so 40 minutes to 1 hour long. And we have 27 games where so every player, every participant in the game is essentially paid some money to participate. But there's an extra incentive for them to there's extra monetary incentive for them to win. So they're given, I think, additional $10 or $20 if they also win. So they are well motivated to participate, and they are well motivated to win. So each round in each game, essentially, when at the beginning of the game, people are assigned roles individually, and as we discussed, spies know who the other spies are, and non-spies do not know who the other spies are. So this was the game setting. We had people sit around like 8 small tables. Each one had a tablet in front of them that would record essentially the face and like some upper like the shoulders and stuff from each of these players, and we recorded essentially the entire game. And let's take a quick example. So these are 8 people from one game. These are interacting. These people are interacting with each other. One of these columns has 2 spies, which are deceptive people, and let's see if you can actually identify who the spies are. So it's a very short clip, I think 5 seconds long. Supposed to be audio.
Yeah, I think it's playing.
It's playing, but it's supposed to have audio. That's fine. Let's see. So playing it again. So how many people think it's column 1 or column 2? Column 1 is 1, 2, 3, and 4. Okay. So I guess one person is right. It's column 2, and if you see, it's very hard. First of all, because I only gave you like 5 seconds of clip. People have 20 minutes, or 1 hour to actually figure out who the spies are. So this player was actually very was only looking at the tablet in front, was not interacting, while this player was actually looking around, figuring out what the other players are doing. One of these players was speaking. So there's no one strategy that the spies use to essentially deceive others. But what is interesting is that, as I'll briefly allude to in the future part of the talk, when we use networks, we can actually identify who these spies are from short video clips. Yeah.
So can I just ask a quick question about the groups that are selected for this? Do they know each other before this experiment, or are they just meeting each other for the first time?
They may know each other. I don't think there were any constraints that were worked.
Okay, because the only thing I can see with that is if you know someone for many years, you're probably a better lie detector on them, or a worse lie detector on them. If you're
That's a great observation. So I think that is one of the variables that we are testing, like as future part of the research on, like, if you know someone from before, like whether you are able to identify deception by being done by them very accurately. And we, like, at the beginning of each game, we actually take surveys. So we say, do you know, like, every pair?
So you have that data, but you haven't controlled.
Yeah, we haven't studied that. Yes.
Do you actually have any special tasks if you're a spy, or is it just a label that's applied to you?
It's just a label. You're free to do whatever you want.
You want the hidden.
You just want not to be identified.
So if you're able to forget that the label has been applied to you, then you're presumably fine. Then you can
Technically, yes. Technically, yes. But then you're not helping your team. So you still want to get more votes for spies, but you don't want to give away that you are a spy. Okay. So for people who just joined, welcome. And I'll just give a very quick overview of what I've talked about. So it's we have collected data from 27 different games of one particular game called Resistance, which is a deception-based game. And now we just gotten started with looking at this data. And the goal of this talk is to extract networks of interactions from these videos. So people are essentially sitting around the table. They are talking to each other. There are 2 groups of people. One set of people are spies who are deceptive all the time. Other set of people are non-spies who are honest. The task of non-spies is to identify the spies. What we do is use these videos of individual people, to create networks of who is looking at whom, who is talking to whom, and so on. And then we finally use that to predict deception. Okay, so let's see. Okay, so this was the data collection part, and now we essentially have 27 resistance game videos, and we'll look at how we can actually leverage these to extract networks. Now, as I was saying before, people have used individual video analysis or like computer vision techniques to identify whether one person is lying or not. And the problem with that is it doesn't really figure out who is interacting with whom, or who is talking to whom, or like who's shouting at whom. And these interactions are important because these create understanding these interactions is important because it gives additional information than just individual person analysis. So it gives you dyads instead of single nodes. And previous research has shown that this type of interactions, these non-verbal interactions, are indicators of dominance, trustworthiness, deception, and even group success. So the reason we extract these is to predict these things, and we can also augment these networks with additional information like emotion and like whether and for other downstream tasks. Yeah.
So based on the rules of resistance, or when you're in an intermediate stage of the game, not everyone is just based on the rules of the game equally likely to be a spy, right? So for example, if two people put cards in the middle and one of them's red, then there's a 50% chance that either of them is a spy. And so did you control for that, or does that might likely affect how dominant or trustworthy or any of these qualities one person is exhibiting at a different point in time?
Sure. So we have not studied that yet. We are still actually at the stage of network creation, which I'll talk about. But that's a great point. One thing I want to remind though is roles do not change over time. So roles are assigned at the very beginning and they're constant for the entire game. So, but those are great points that we should look into. Thanks. Okay, so the prediction task is for every 1/3 of a second, we want to predict who is looking at whom. And this is a very, very short duration of time. The reason we choose this is because prior literature says that it takes us 1/3 of a second to focus our attention on someone. So essentially, 3 times in 1 second, you can actually look at 3 different people. And this is actually called focus of our attention. So the prediction task is predict the focus of attention, and each player has multiple different options. So they can either look at other players who are sitting, they can look at the tablet that's in front of them, or they can look at like nothing at all. So the task is for every 1/3 of a second, predict who every person is looking at, and this is really, really challenging. So here I'm showing essentially 1 second screenshots from 1 second of one player. In frame 25, this person is looking at player 6. Then for the next 2/3 of a second, it's looking at player 1, and then it's looking at she's looking at player 7. So in 1 second, this particular player is looking at 3 different people. So it's a very, very challenging task to extract the focus of attention. And the second is non-verbal behavior actually impacts who we are looking at and the focus of our attention, both verbal and non-verbal. So for example, in this particular frame, this player was speaking, so everyone else is looking at it. At other point, if let's say I start waving my hand rapidly, other people might look at me. So both verbal and non-verbal behavior impacts everyone's focus of attention. So how do we actually use this multi-person interaction videos to predict who is looking at whom? And to do that, we create a model called video to net, which essentially converts a video to a network, and it's a machine learning model. The core idea of the model is where one player is looking at or one person is looking at influences where others are looking, and is also influenced by where others are looking. So what we do is we simultaneously predict everyone's focus of attention instead of predicting each one's focus of attention individually. And it's one of the first models that actually does this joint prediction of sorts. So our model actually is quite simple. It's inspired by a recurrent neural network model, but it's not a deep learning model because we don't have enough data. But it's a simplified version of that. So what we actually have is we create one classifier per player. So my classifier is different. If I'm part of a game, my classifier is trained separately from everyone else. And it has two different components. One is a collective classification component, and the other component is a temporal component. So the collective classification component actually builds in this player-to-player interdependency, where a player P is looking at time T depends on where everyone else is looking at the same time. And the temporal component actually, what it does is it smoothens my predictions up. So where player P is looking at, it will depend on where player P was looking at the previous timestamp. So to be more concrete about what the model does is, let's say you have three different players. So this represents one classifier, the classifier for player 1, this is the classifier for player 2, and this is the classifier for player 3. The input to these classifiers are raw like head, pose, and eye gaze vectors for that particular time. So this vector would be player 1's head, pose, and eye gaze vectors, which are essentially extracted using open source code called OpenFace. So we use OpenFace to extract head pose and eye gaze of each individual player at every frame. Then what we do is we create this collective classification component. So this is pretty simple, where every classifier of the player, in the first layer, it only takes as input the head, pose, and eye gaze vector. But in future layers, what it does is it takes the prediction made by the other classifiers or the other players as inputs to modify its own prediction. So let's say individually this particular classifier might predict that this player is looking at player 5 without taking into account where everyone else is looking. But let's say everyone else's classifiers actually would modify it to say, hey, it's not player 5, it's actually player 4 or player 6. So what this collective classification component does is it takes the output, the prediction made by the other players, and uses them as input in modifying its own prediction. So that's the collective classification component. And then we have a temporal component where the same player's prediction at the previous time. So let's focus on the red block here. So this is the prediction made for that player in the previous timestamp, and that is used as input in the next timestamp for the player. So what it does is it is aware of what the predictor predicted in the previous time to modify or improve its prediction at the current time. So that it doesn't really predict like 5-2, 5-2, 5-2, for example, but it would rather be like 5-5, 4-5 or so on. Yeah.
Does this mean 1/3 of a second before?
So this is per frame, and then we like aggregate it for doing it 1/3. So 1/3 is essentially 10 frames.
So every 10 frames or every frame like?
So we predict for every frame, and then we have an aggregation layer on top that would aggregate 10 frame predictions into one prediction. Yeah, that's a good question. Okay, good. So we have the problem here though is we don't have any actual data or like labeled data to train our model to make this prediction. So what we did, what Chongyang actually did, who is the PhD student who led this effort, was he manually annotated about 2 hours of this videos to get about 8,000 labels. So he looked at these videos and like made manual labels for every 1/3 of a second. Very, very tedious task. It took him essentially 1 week, full 1 week of work to get this done if we actually worked 8 hours per day for the entire week. So this is a very, very time-consuming and tedious process. But the goal of our work is for nobody else to do this work and just use Chongyang's efforts to create a model that can reduce work for everyone else. So what we do is using this model, I'm actually showing here, it was a bit quick, but this is essentially the demo of our model. It's slowed down, I think, 1/10 of time. But what essentially it shows is that for every player, we have prediction values for where the player is looking at. We also predict at every frame whether the player is speaking or not. And here is the final network that we extract. So essentially, at this particular time, everyone is looking at player 7, for example. So this and individually, this is like the prediction made for every frame for every player. Let's look at an enlarged view. So it's a different view for the same set of people. This gives you the same information without all the numbers. So this is the input video. Let's say actually the input videos are the tablet versions of these players, and this is the network of output. So you see that the nodes are the same essentially because players don't move, and each edge at every point of time shows who is looking at whom. And what you see here is that it changes rapidly. Like every second, you would have a different sort of network. And the task that we have and that we are working on right now is using these networks, not just from one game, but from all the 27 games that we have collected, using these networks to create a model that can predict who is being deceptive and who is not. Actually, in this one, I think this player was deceptive, and can't really say from the networks without any labels or any training, but this player and I think player 2 was also being deceptive. Yes?
So since there is a asymmetry in the information games, meaning spies know that they're spies, and but the non-spies don't know. Did you find this asymmetry in the result of the gaze also?
That's a great question. Just to give information to everyone though, spies know their identity as well as who the other spies are, and non-spies only know that they are non-spies. They don't know everyone else. That's a great question, and that was the first analysis that I did, that we did before going to that. Yeah, so what we found essentially was that since spies know who the other spies are, they tend to avoid looking at them, and they tend to not avoid speaking to them and interacting with them. While non-spies who don't know the identity of everyone else, they essentially interact and talk to like both spies and non-spies equally. And that is like, I think I found that last week when I was analyzing these networks. So this is like fresh result, and it's statistically significant and everything. And we found this using like these networks and behavior features and all like multiple different sort of metrics. But that is the reason why we have created these networks, is because so that we can find these insights and then use these for prediction. So that's a great question. Thanks for bringing that up. Yeah. Any other questions before I move on? Yeah.
So how do you think this would kind of generalize to outside of the domain? Because in this case, are we going to pull everybody into groups of 7 people and then have everybody stare at each other and try to figure out who's the liar in the room? Because under that, like everybody could say, well, you're being deceptive because everybody in this room is looking at you. So I don't know how it easily transfers out of this domain.
Right. No, that's a great question. So right now, so the model itself is pretty general, where you can take the model, you can fine tune it to people standing or moving around and so on, and there you can train the model to create these networks at every point of time. But you do need the training data at that for each individual setting. You do need the training data for who is deceptive and who is not. So we particularly tested it for this one game, and it's more like a proof of concept rather than like a complete package of solution. But like this video to net method is kind of general, and you can apply it to like other settings as well. Okay. Of course, we need to see whether the model actually is good or not. And to do that, we did a bunch of experiments where we tried to predict like where I'll be looking at in the next k time steps. So we use the data till time t, and we try to predict the focus of attention for time t plus k for every player. So what we do is again k is a multiplication of 1/3 of a second, and we essentially train till about 96% of the data and predict for the next t plus kth moment, and we vary k. So when we have k equals 1, that means given what we have done, what we have predicted till now, where people are looking at till now, can we predict where people will look at in the next 1/3 of a second? And compared to 3 very strong baselines, we outperform the strongest baseline slightly. But when we do prediction for future, so this was like predicting just for the next 1/3 of a second, and this is when we predict like 3 seconds in advance. Can we predict where everyone else, where a player is looking at? We see that the performance improvement over the baselines actually improves a lot. And we did more experiments to figure out what gives this particular boost in performance. And what we found is that the most boost is due to the collective classification component rather than from the temporal component. So temporal component adds, but when you add the collective classification component of being aware of where everyone else is looking at, that improves our predictions a lot. If you remember, we have these individual baseline classifier. We have individual classifiers for each player. We tried lots of different classifiers to make these predictions, and random forest classifier turns out to be. No explanation of why that is the case, but so in conclusion for this particular part, Video2Net, which is our model, is essentially able to extract these networks from videos of people sitting around a table and talking to each other. Now, what I did not show in this part yet is that we can actually augment these networks by adding speaking relations. So if you just create this network and add the information of who is speaking at a particular time, you can extract networks of who speaks to whom. You can add emotions. So there's OpenFace, this amazing tool, open source tool, where you can use, you can extract whether I'm smiling, I'm calm, or I'm angry, and so on. I can augment this information into this network and create a network of who smiles at whom, who shouts at whom, and so on and so forth. So like without these additional layers, you get the information of who looks at whom, but you can obviously augment it with a lot of different things. And as I just answered, using these networks to extract insight gives you a lot of information. For example, that spies avoid looking at each other and speaking to each other, while non-spies don't do that. So right now I talked about the first 2 steps. We are still working on reasoning and predicting on these networks. Hopefully I will have it by the next KEG workshop, and happy to take more questions. So yeah, thank you so much for having me, and thank you for listening.
So by the collective thing, I think you mean, let's say you have 7 players, and you determine that 5 of them are looking at player 1. Now you're trying to resolve the final player. And there's a question of the model may say it's either player 1 or player 2. And by you knowing for sure that the other 5 are looking at player 1, you're more likely to think that one also going with player 1.
That is how, theoretically, yes.
That's what you're doing.
Yes, that is what the model should learn.
To break ties.
Not so. The model would, let's say there's one player who always agrees, like looks at where everyone else is looking at, then the model would learn to also predict player 2. But let's say there's a player who always doesn't, like, looks at someone else instead of where everyone else is looking at, then the model would learn to not predict player 2. So the reason is because we have one classifier trained individually per player, so we can essentially fine-tune for the behavior of this player individually. If we had a general classifier, like instead of training one classifier per player, if we train one classifier for all players, then it would try to do this tie breaking. But in our case, it gives additional power to the model by doing it separately. Yeah.
So I'm kind of curious, what happens if you apply this model to other games? For example, like in game of poker, there are there's so much video in YouTube that you can also know that who's bluffing.
Yeah.
And so I wonder what happens if you apply this to those kind of video
That's a great idea. We have not tried that, but we can. That is definitely that we can try. And we are also looking at expanding this beyond games and looking at general scenarios, meetings, for example, talks, for example, and so on. So that's looking at poker is definitely really interesting, and maybe we can win money, like we can make money by using this model at some point.
Maybe more reliable than applying for grants. I have a question. Do you suppose it would be very difficult to transfer this to domains with moving agents? For example, first-person games or third-person games?
Yeah, great question.
Where like avatar gaze is actually part.
Right. So if the player is moving it, you need to extend this model where you need to have like a spatio-temporal component. Like we already have the temporal component, you need to add like a spatial component to this particular model. But that's a great idea. I think this also ties back to your question earlier, whether how extendable this model is, and definitely adding the spatial component, and also like considers meeting scenarios where, or like let's say we put a camera or 10 cameras in this room, and for the social gathering event, right? And then people are forming groups and breaking groups and talking to one another. So those are really interesting problems, and we have not looked into that. There is some work on trying to figure out who are standing next to each other. I think there's a lot of work from MIT Media Lab on that. There's also a public data set. There's also a recent data set from a university in Germany. Sorry, I'm blanking out on the name. But if people are interested, there are essentially data sets on people interacting with each other. But yeah, we have not looked into this particular, like extending this to spatio-temporal interactions, but that's a great avenue.
Yeah, I guess the key question is like, do you assume the sort of uniform distribution of people around a circle, or just like some feature that tells you the direction of people?
Right. Yeah, I think in a general scenario, this would not be uniform. Actually, in our case as well, there may be some seats that are empty because we always have 8 seats and there may be 5 players. So the model kind of learns, but in a more general setting, that may not obviously.
Good enough.
Trying again.
Hey.
All right.
All right. I know that the video is turned around so you can see everybody else but me.
Are you really there then? Is this an A?
Yeah, am I really here? But Matthew can't be seen in a workshop. Is he really there?
I mean, it could just be NVIDIA's like face scan thing at this point.
That's true.
Although
Okay, now everybody's gonna be able to see what I see. Hopefully. I might have to change the source again.
video just froze for me.
Yeah, it'll be in just a second. There we go.
It's much brighter now.
Well, that's because the screen's all turned on. Hopefully you can see some friends. They're in the or some enemies.
Well, it depends. Are they reviewing my paper or not?
Hold on, you're writing papers again?
I didn't say that.
All right, I think we're good to go on our end, as long as from your end the audio isn't too echoey.
I don't hear any echo. Do you guys hear echo?
No, okay, then I think we're good to go whenever you are ready. Oh, I guess I should say real quick, this is Alec Zook. He is joining us from across the pond, I guess, over in California, where he works as a data scientist at Blizzard. So we're super excited to have him for a sort of distinct perspective on this problem from all the other talks that we've heard today. Right, whenever you're ready, Alex.
Alrighty. Let's start from the beginning of the slideshow, maybe. Oh no, preview. All right. Are you watching my screen, or do you actually see the presenter view version?
Right now, I'm seeing your face.
Hmm.
You should be able to share screen, maybe. Give that a shot.
Screen share, application window. Why? Whoa, you can see what? What happened?
Still seeing your face.
For a second there, it showed me a bunch of things, and then it went away. Ah, fuck you.
You are being streamed to YouTube, so just be aware of your language.
Sorry about that. Can you see it now?
Still no.
What? Okay, now it's telling me what I would like to share is an application window. Now populate that. Populate that.
Maybe you can be closer to the screen so we can see it in your glasses.
Can you see it now? I'm getting a video call from you.
That shouldn't be happening. I don't know why that would be.
All right, let's just try.
Wow.
All right, so that was half the talk, the better half. I'm coming, as Matthew kind of said, from Blizzard. I'm one of the data scientists there. I'm just going to talk about a couple of cases of ways we look at some problems in our games through the lens of data science. So for those of you who are not familiar, Blizzard makes many games. I think we're up to 28 years now of making games. And those range from, World of Warcraft, which is a multiplayer online game, to Hearthstone, which, is on mobile and console, etc. Overwatch, which is more a shooter, Heroes of the Storm, Diablo, StarCraft. The point being, in our games, we care a lot about data science because these are all sort of live services that never die. Like, they're still supporting Diablo 2. So we don't really get rid of old things, which means we care a lot about continuously improving and iterating on them, which is where then it really helps to have a perspective from an actual extraction of knowledge from these games, whether that knowledge is about player behavior or how things we've done in the past have worked out, etc. So first off, data science is kind of an industry jargon term, so I just wanted to clarify clarify what I mean by that. So broadly speaking, we have AI and machine learning, and they're related fields, and depending on who you ask, one's subsumes the other, and that's a fun sort of culture war, but it doesn't really matter to me. From our perspective, really what we care about is this big umbrella we call data science, which is quantitatively being able to understand what's going on in our games. In the world at large would be great, but the games is good enough, and as well as predict various things going on, which means we certainly work with techniques from AI or machine learning, but also techniques that might more naturally fall under statistics or theoretical or applied math, even ideas from neuroscience, psychology, graphics, vision. Like, these are all fields we employ people from at Blizzard because we really want a diversity of perspectives on this problem, because the reality is we don't care where the tool comes from as long as it solves the problem. So the question then becomes, like, why do we need data science? We broadly use it for two sets of things, right? Game design and business. But the key thing being we have this big, like, multi-ton statue sitting in the middle of our courtyard that says gameplay first. So that's actually, like, the core driving value. So I know many companies talking about business will be, how do we basically squeeze people for a lot of dollars as quickly as possible? Our focus is far more on how do we make the best possible experience with the expectation that this will have downstream consequences that are good for us, especially for our players sticking with us, because see, earlier point, we keep our games around a very long time, so we don't want people feeling like they can't trust us. In this talk, I really want to focus on just two examples that are more on the game design side. One is around how we use data science to help support matchmaking / feature balance in Heroes of the Storm. And then the other is around how we're using sort of data science techniques towards sort of segmentation and understanding our players in Hearthstone. One big caveat, I've had to do a little bit of stuff to sort of fuzzify the data. So trend-wise, etc., like, it's plenty understandable, but we have, like, really rabid fans. So if any number comes out there, they go nuts. So we want to be careful not to have any number we can't, like, really rigorously defend and spend a long time on Reddit defending. So that sake, a lot of the numbers here are a little bit fudged just to make things easier to talk about. So first off, Heroes of the Storm matchmaking. Heroes is a 5v5 MOBA like League of Legends or Dota 2. And in these games, you basically have two teams of people form up. The mechanics don't really matter for our purposes, but the point being we want to keep track of how good people are because we want to put them into matches that are as fair as possible against each other. There's a whole lot of different game modes in Heroes, but for our purposes, we're going to focus on the subset that use some estimate of player skill to actually make those matches. So obviously, when you're facing AI, it's a different question, or if you're playing custom games, we may have different constraints. But the things I'm talking about here broadly apply to any of our sort of skill-based game modes, whether those include an explicit ranking or not. This gives an overview of sort of how matchmaking works under the hood. Where players have some skill estimate that we keep track of, as well as an estimate of the uncertainty. We call that skill estimate MMR. So if you hear me slip into saying MMR, I'm just saying, like, our current estimation of how good a player is at Heroes of the Storm in that particular game mode. Matchmaking basically lets players first form their groups. In one of the game modes, they get to choose their character beforehand. In the others, they actually have to go through a drafting process later. They'll enter some queue. That's where we start taking over. So we'll actually, the orange cells here are all the ones that data science is involved with. So there's this process of assembling teams. So we know how good players are, stick them all together into teams, as ideally as quickly as possible as well. Look at how good the match might be. Shuffle things around if we need to try and make the match better or good enough, and eventually let the match happen, and then you get the final step of updating the ratings of the players after we've seen what happened. So if they win, we say, hey, you're probably better than we thought you were. If they lose, we say, hey, you're probably worse than we thought you were. If you're me, that's most of what you hear. For this talk, I really just want to zoom in on one particular part, which is how we estimate the notion of match quality. So match quality can mean a lot of things to a lot of people. For Blizzard, the real thing we care about here is fairness. Meaning, in expectation, we want you to have 50-50 odds of winning that match. So that kind of sucks from a psychology side because players would very much like to win, like, at least 3/4 of their matches. But there's no way we can do that for the whole population without doing things like throwing in bots you play against, etc., which introduces its own problems. So here I'm going to talk about a few iterations of solving this sort of 50% expected win probability, starting with a sort of handcrafted utility method, and then two methods that were data-driven as opposed to sort of more eyeball-y. So this first eyeball-y approach was utility, which was we defined a function that was a combination of various pieces of data we would have on players when they entered the queue, and use that to try and estimate how good a matchup might be. And these utility scores could then be used to evaluate, do we think this is going to be a good matchup based on their closeness? So some of the features here would make sense just intuitively in terms of the differences in the skills between the two teams, the differences in our uncertainty in those team skills, how widely spread they are. So because players can form their own groups, we don't always have full control over the skills of the players. So you could have someone who's carrying the other player, meaning a really good player is playing with someone really bad, trying to make the match work out to their favor. Wait time then and latency are more of external factors. So wait time is if you've been sitting in the queue a long time. Latency is just a factor of the players themselves. So high latency players playing against low latency players don't tend to like that because they're sort of unevenly matched in the actual like network statistics of the game. And then party size, which is sort of the size of pre-made groups, because again, we kind of expect that independent of our estimate of a single player's skill, there is some factor corresponding to how well people who know each other can play the game better than we might expect from their independent ratings being subbed. So we defined this function, we used it for a while, made a bunch of matches, and we actually did tune it to some degree based on data to the best we could, but it was always a manual tuning process done by some of the matchmaking designers. So this is the outcome. So the axes here are both the win rates of the players, and the biggest circle is at 50%. And then the rest of this is bins of win rate bucketed together. So what these bins each represent is we bucket a slice of matches that have nearby win rates, either in terms of their expected win rate. So the expected win rate is based on the utility calculation where we think their odds of winning should be. And then real is we pull all the matches that have that expectation and calculate what is empirically the actual win rate. So the diagonal line is, the diagonal is if the expectation thinks it's 50%, that's at 50%. The size of the circles corresponds roughly to the number of players in a match. So the big takeaway from this is the bulk of players are sort of near this middle two big circles. Can you see the mouse pointer?
Yep.
Awesome. So most players are getting pretty close to 50% win rates, but there's more of them than we expect. And their win rate is slightly higher than what the model thinks. The big problem is that while this is the preponderance of players, so things are overall pretty good, there's some divergence around the tails. And so we're seeing these sort of long tails that start getting really different win rates, where good players actually have a much better win rate than they should, and bad players have a much worse win rate than they should. That's not really what we want for obvious reasons. So the question is, how could we improve on this? The obvious answer was to actually do a model, in this case, a relatively simple one called logistic regression. For those not familiar, logistic regression is a model used to predict discrete outcomes, in this case, winning or losing. And we can tune this model using a number of features from the team. So basically, this subset of features here is an example of some of the kinds of features we feed into the model. We're trying to have one that doesn't overfit for obvious reasons and basically predict the outcomes of matches. What is nice about logistic regression is that while it's trained on data that has a discrete outcome, in this case, winning or losing, the actual model outputs of a prediction are always a probability. We can use this to estimate what probability do we think players will have when in a certain matchup, and then evaluate a set of those possibilities and pick the ones that are closest to 50-50. What we actually did was, and so this is the outcome of applying this new logistic regression model. You'll see that the matches are spread out more, but they're much closer together in general. This was due both to using the logistic regression model, but also slightly loosening the criteria to allow a band of win rates rather than precisely 50-50. One of the nice side effects of this was dealing with a related complaint about really long queue times. The problem being the longer we search, the better your match will be, but that also means the longer you're sitting around waiting to actually play the game. So what this chart basically is showing you is, by comparison to the utility case, we spread the players out a little bit more over a range of win rates. We brought in the sort of closeness of matches very, very substantially. So overall, like empirically, this looked like a good thing. And then when you go to Reddit, they complained less about it. So we must be doing the right thing. But there was a problem, which was what I was showing you was sort of aggregate population level statistics. And this is one of those challenges in any sort of data-driven approach. But really, this is a standard AI problem of like what you represent is what you deal with, where the prior model I was showing you was aggregates across the population. Whereas what we actually care about in some sense is not just the win rate overall, but the win rate based on sort of how much you've played. So each of these colored lines represents, roughly speaking, a band of player experience. Hero level was a progression you could make based on how often you were playing. It would go faster if you were winning better, but ultimately you can kind of grind it up. So what these lines are showing you is what are the win rates once you break out each individual player, or you bin players out based on what level of progression they've made in the game or how much time they've invested. So the key point here is the red line is what we expect from the model I was showing you earlier. Each of these colored lines is basically showing that from lower experienced players are having much lower win rates than we would expect just based on the model, while higher experienced players have higher. The solution here is pretty trivial from a modeling perspective, which is just to include the hero level into the model and then ensure that you regularize the model enough that it doesn't overfit to that data. And fortunately, because there are relatively few heroes compared to players, we can use that to get a much better model. So this is the outcome of doing that sort of adjustment to the model, where now most players, all the colored lines are stacked on top of each other because more or less independent of skill level, you have the same expected win rate. And that's because we're now accounting for the level of the players on each team. So just again, for comparison, this is the before and after, before on the left, after on the right. The key point here is this is sort of a very iterative process, and this is going back to that earlier point, where we're always trying to account for what else could we be missing that we can appropriately account for while still dealing with issues like the fact that every time we change the game, some of these things will shift under our feet. So we don't want to make too specific of features in our models that will then become useless when something changes. So if we had a feature here, for example, for every hero, or we tried to tune per every hero, every time a new hero comes out, we'd have a cold start problem of dealing with this new hero when no one else is there. We'd also have issues around all the other heroes potentially being changed in how effective they were based on their interactions with that hero. So while it sounds like a great idea on paper to throw in every feature possible, it often means that in practice, because these aren't just models fit on static data, but a live feedback loop, we need to be really careful on some of those things. So this isn't the work that I alone did. I just wanted to acknowledge a whole bunch of different people have contributed to this project over time, and it's changed hands many times. And these are just the data scientists I'm showing on the slide. Jens is the exception. Jens is a software engineer who's helped us a ton with all this. So that's just within my department, within my group. There's a huge amount of work that has gone into this from the game design side, the engineering, tooling, production, the community team, etc. And the point here I just want to hammer is that in a live system, there's a lot of parts involved and a lot of moving pieces, and that often adds some interesting constraints to the problems we're trying to solve. So before I go on, Matthew, do you think I should take questions now, or do you want to wait and just pull them all together at the end?
People have
All right, cool. So next topic, the meta in Hearthstone, which is the sort of, well, I'll get into that. And this is much more oriented towards supporting design, but we believe it has a lot of interesting downstream applications that make it an interesting problem. So what is Hearthstone? Hearthstone is a card game. Two people play against each other. It's similar to Magic the Gathering if you've played that and you're not familiar with Hearthstone. This genre is apparently still popular with PvE versions like Slay the Spire and Artifact from Valve most recently. Point being, what really matters from all this is the gameplay is around playing cards against your opponent and trying to defeat your opponent. But for the purposes of what we want to understand, we actually want to understand the strategic layer, and that comes in before the match even starts. That strategic layer is around how you use your collection to build the deck that you go into the match with. So what we really want to understand is what are the decks players are using, and are those meeting sort of our expectations for the ways people can play the game and the way those decks actually play out in practice. So what I want to cover is what we mean when we say the meta. Players mean similar things sometimes, but not always. How we actually approach balancing the meta. So the goal is that the meta be balanced, but what does that actually mean and how do we do it? And then ultimately, you know, because we're trying to provide this quantitative lens on it through data science, what are we looking at when we're trying to make some of these, at least data-driven components of these decisions? So first and foremost, what do we mean by the meta? The meta is short for the metagame, which broadly speaking in any game, we're talking about strategies used by players. When I say strategies, I more or less mean the sort of big macro slow-moving decisions, often decisions you make before entering the sort of more intense match of a game. So in Hearthstone, that would be the sort of deck composition. You could imagine in Heroes or Overwatch, it's your choice of team. It's anything that's a sort of slow to move component that really dictates your set of options once you go, in Hearthstone's case, pilot a deck. The left and right show two slices of our player population split differently. One is purely by class to just indicate rough proportions of these classes. The one on the right then breaks out these classes into what the ultimate outcome of this analysis is, which is the sub decks within the meta. So we break out a druid into an aggro druid, for example, as well as a few other types of druids, and the same applies to each of the other classes. What we'd like to do is be able to say not just what class is a player playing, which is already apparent from their choice of class at the beginning of when making a deck, but rather what are they doing with that class. So what does it mean for a deck to be healthy? In our case, it means that we have overall a wide diversity of decks that are relatively fair in the sense of, again, that 50-50 win rate against each other, at least on balance, and fun. So the comic there for those who are not familiar with Hearthstone is basically making fun of the fact that at one point, one of the powerful decks was not particularly fun to play, but was also very effective. And in general, what we want to do is avoid that being the case, because that means the person playing the game feels like they're doing the same thing all the time. The person that is playing against the person playing the game is also feeling like they're doing the same thing all the time. And that particular deck actually matches would last an exceedingly long time, so it drags everything out. So how do we balance the meta? Really, we want to address those three concerns, right? Diversity, so the meta should feel like it's dynamic and changing. So it shouldn't feel like all the time you only have one option of how to play the game, but that over time that evolves. Other people introduce new strategies, you have to develop counter strategies, etc. Fairness plays directly into that. If there's a deck that's just always the best thing to do, that's really boring to actually play against, even if it might be fun to try and design a scenario like that. And finally, this should be fun. So even if a deck is really strong, it's really boring to play at some point. We would hope that it doesn't remain in the meta, and we may want to intervene if that's becoming the case. Conversely, if a deck it doesn't have a great win rate, but it's really fun, it may be okay even if it's not super powerful. Ultimately, the way we kind of approach this is a combination of feedback from the players. Reddit is one example of that, but everything else, our forums, on Twitter, the designers really go out of their way to make sure they're listening to everybody involved. Designers' intuition, and then, of course, the part that I care about particularly for this talk is data on what actually happens. So the product from all of this is what we call the Hearthstone Meta Report, or the Meta Report. And this is basically an overview of the state of the meta at any point in time. Over time, the sort of complexity of this report has evolved, as well as the frequency of updating it. So we're trying to go for basically an automatic report so that any day if you pull it up, it's recognizing what's going on in the meta. So what we're trying to do at a high level is assess the popularity of different decks, then get a sense of things like their win rates, and then also understand some of the counters in terms of the win rates of one deck versus another. So for example, in the report, if you were to pick Aggro Warrior at this time, you wouldn't know that it's just a roughly 52% win rate, but also how well it did against other decks. So it's very strong against the Quest Mage and Quest Shaman at the time, although there aren't very many games there. and is really countered most heavily probably by the aggro druid, and maybe tempo mage as well. So this gives designers an easy way to sort of get a sense of overall what's going on, and then inform their choices of where to intervene and when. So the first big problem is, of course, how many decks are there in the meta? The easiest answer is there's one for every player, but that's not very useful because there's way too many players. Another would be every distinct deck, but again, that's still not really useful. So how do we actually know how many decks are in the meta? Are there really always a fixed number? The answer is probably not. So then how do we cope with that? Once we know what the archetypes are, what's in them? It's not good enough just to know that there are 1 or 2 or 3 or 10. What actually cards are being used in those archetypes? How do we understand some variants of an archetype? So even if we know what the primary one is that the only way to play that, or can you swap out cards? If you go to player guidance sites, they'll often say, you can play this deck, and then you have an option among a few different cards depending on what's available to you. What about new decks, right? So what about the ones that aren't yet really established archetypes, but are emerging or something that we might want to understand more about? So as an example, this is kind of the output of the algorithm. So what it's going to do is basically try and pull together how many of each card does a deck have, and into one big vector. The number of cards that are actually being played in Hearthstone varies a lot over time, but it's on the order of about 400 different cards. So that's going to define in our data a dimensionality of about 400 columns. So 400 different possible cards that you could have up to 2 of, sometimes only up to 1 of. And you need to construct a deck that has 30 cards. The approach we're going to take is, again, fairly standard machine learning approach of using clustering. So the idea of clustering, for those not familiar, is to basically group together different things that are like one another and dislike other groups of things. So it's an unsupervised learning problem. This example is showing you in a case where the data only comes from 2 dimensions and they're continuous dimensions. But you can imagine cases that have different numbers of features, etc. Clustering is a whole research area. It's very hard to establish great ground truth metrics, so it's a very challenging problem to work on in many cases. Especially for us, this becomes a problem because we want relatively few decks, even though it's much easier to split data into many smaller groups, despite that not being too useful to us. So the particular model we ended up settling on after trying a great deal of them is a Gaussian mixture model, which is basically summarizes each deck using a sort of Gaussian bell curve shape. So if you're familiar with that, it's this sort of normal distribution. The idea is we'd like to fit our data into a mixture of these underlying Gaussians. So we're making this continuity assumption, which lets the decks sort of overlap in clusters and has a few other nice properties. You still have to make choices about things like how you constrain the covariance matrix. Is it spherical, diagonal, etc.? There are quite a few free parameters here. And because there's no ground truth labeling that we can use, it does mean that we have to do quite a lot of iteration and then sort of examination of the results. We've settled on one that seems to reliably produce good results, but that was kind of where this comes from. If you're interested in the math, you can always go look it up. Again, it's not particularly sophisticated or cutting edge, but it turns out even compared to many of the more cutting edge algorithms to reliably produce the most robust results. Robust meaning like if we run it 3 or 4 times across very slightly different data sets, it doesn't change its mind. What GMM is doing, roughly speaking, in 1D would be sort of fitting this red curve to the component blue curves, or extracting those blue curves out. In 2D, it's sort of this notion of fitting these fields of points together. All we're doing is just adding like 398 more dimensions to that and trying to do it in that space. So when we use this clustering, what we're using as input is every single deck we're seeing. So a deck here is a row, and the columns are the cards that would make up that deck. So each one of these is a unique deck that at least some player is playing, and that gives us data on which cards are in that deck. What we'd like to do is group them together so we have sets of decks that are all more or less the same. So in this example, the boxed out section is something that the clustering identified as a cluster. You'll see that it shares many common cards like Flame Imps, Soulfire Voidwalkers, etc. This is basically a really old Zoolock deck from back in the day. And we will also come up with other decks. And so what we'd like to do is partition all the decks into a space of a relatively small number of clusters. The nice thing with Gaussian mixture models is you can use various metrics of model fit to assess how good it is and vary the number of clusters rerunning and clustering each time. GMMs are relatively quick to fit, so we can actually run it on many different numbers of archetypes and then pick the archetypes that have the best overall fit to the data. So it might be one class has 3, another has 10. So once we've done this exercise, we finally have the decks from the meta, and we've labeled every deck that's out there to one of these decks that we've partitioned out. We manually go through and actually label these initially, but at this point we can kind of automate the labeling by comparing the content of decks for the most part. Obviously, when new cards come out, we have to do a little bit of additional work. But that gives us roughly this report here. So what you see on the left is that same data from before, just pivoted. So each row is, again, a card, and each column is one of the decks in the meta. So what this is showing is we have sort of 2 variants of what you might call an aggro druid, another, like, I think 8 or 7 of jade druids, and then 1 and only 1 of a ramp druid. If you're not familiar with Hearthstone, suffice to say these are just prototypical ways that pros recognize, and the main person working on the meta report likes to hit legend every season, so he knows a lot of the decks really well. For each of these archetypes, we then aggregated up a bunch of different statistics based on the individual decks. So this view here is showing, compared to sort of a 50-50 win rate, what's the win rate of the various druid archetypes. At this time, druids are really powerful, and this is giving a sense that, yes, they're well above the 50% win rate. And here's a breakdown of what's popular. So one of the interesting things, and this does often happen, is a case where one of the decks with the highest win rate is actually not the most popular. So just because it's very effective does not mean players have caught on. And in fact, the second most effective one is also not as popular as the most popular deck. This could do with a lot of different things, which is why we have many different slices of this data to try and understand it. It could be, for example, that one of these decks is very cheap or easy to make. Could be one is just well advertised among the player community, etc. The last view here shows what counters any given deck. So when you select one of the decks from the archetypes, this will show for matchups, if you are of each of these types of archetypes, what are your overall win rates against other decks? And this is one view of what counters a deck to help designers understand, are there enough counters that they don't need to worry even if the win rates are a little on the high side. This is another view, this one allowing a lot more drill down. So this is actually listing for every de-identified player, what are your decks and what are your win rates and how are you doing overall. So this gives a sense of the very concrete, what is the deck being used. In the archetypes that we find, we may not have all 30 cards. There may be a lot of disagreement about which cards to use. So you could have an archetype that only has 27 cards. This gives an ability to actually look and examine in detail how are the best players or the worst players or whatever using a given deck. Here, this is, for example, sorted by the MMR of the player, so we get that view. Once we have that, we can look in further detail about the actual contents of their deck, where their deck is coming from, their actual individual stats, how they work against different opponents, etc. Lastly, another view, again, focused more on the counters. This just lets you, again, zoom in on a given deck, understand how all the variants of these decks in the meta stack up, look at how well one particular one, in this case, the mid-range Paladin, the Murloc-oriented one, stacks up, and then break out the contents of those. Some of the fun stuff is, because we've been tracking this for a very long time, we can actually go back and get a sense of how the decks vary, and the meta has shifted over time. So on the right is just per class standardizing the proportions of the decks. This is basically that pie chart just shown over time and binned into time period. So this shows the rise and fall of different decks in the meta based on what cards become available. Because, again, we're assigning these relatively macro level labels and we're basing them on deck contents, we can get a sense of where one type of aggro druid might evolve into another type of aggro druid and another, even though the individual cards are not the same. The overall structure of the deck and how it plays is. So you can see these sorts of trends for various classes. Obviously, some decks just disappear from the meta. The changes in the cards are no longer possible to use to make a deck that's viable, and you'll see that happen. We also rotate cards out of use from the game. So this example is looking at the standard mode of the game, which means some of these cards will leave play altogether, which means at least a deck that was strongly dependent on a particular set of cards may disappear from the meta. Sometimes, though, these decks will reemerge. For example, this deck in the Priests disappeared for a while and then was actually able to come back with a different set of cards. The view on the left doesn't normalize by class, but just normalizes overall. So this gives a sense of not just what's popular way to play a Druid, but how popular is it to play this variant of Druid compared to everything else you could be playing. And this gives a sense of the rise and fall of different classes depending on how the cards are structured. Obviously, the other piece of information you'd love to know is not just how popular things are, but how good are they. So this example looks at the popularity of different decks in the meta. You can see the big jumps where decks disappeared from the meta, but this shows sort of the win rates of these various decks over time. These vertical lines here are splitting out the various expansions. So each of the major releases or major patches is indicated so the designers can get a sense of when they make changes, which they know they have an idea of, is it inducing the kinds of effects they're hoping for. So as before, there's a lot of people who worked on this. This one's actually been pretty much in continuous development since at least 2014 or so. So it's changed hands many times and been applied to many things. But again, this is a big group effort. Game design heavily consumes this and is involved in providing feedback, critique, development advice. Data science does a lot of work to actually pull the numbers and compile them and provide guidance. And then, of course, the community team often advertises about decks we've discovered in the game, etc. This report powers those sorts of insights. Just sort of zooming back out, data science is about this notion of sort of understanding and predicting things in the world. What does that mean? So broadly, there's these three categories. This notion of what's involved in gameplay, what's involved in sort of our adoption of various infrastructure and automation methods, and then what can we do for business as well. So in gameplay, we already talked a little bit about sort of informing designers to optimize balance. There is a blog post about how we actually help automate that process for the Hearthstone Arena. So you can go look that up as well if you're curious. We talked a little bit about measuring skill, and we also often use simulations of matchmaking or other systems to help inform changes before we make them, especially if those are larger changes. We don't want to redesign things like a ranked mode without some notion of how would this affect player progression. We also are using data science for things like detecting important events in the game, or in Here's the Storm, this actually powers one of the features in the game where little things will pop out and tell you how well you're doing. That's based on data science models. On the other end, on the business end, that's everything from personalizing your experiences when you're looking to buy things, as well as predicting the obvious things that the business cares about, of things like, are you going to quit the game? If you are, maybe we should be worried if we're seeing overall players are starting to quit more often. We may be able to email people and let them know about features we think they would be interested in playing before they quit. Spending has similar related work. There's been a lot of talk about our work against toxicity and detecting toxic chat. That's all a data science model that runs live on those things. We also work, of course, to detect fraud because people like to do fraudulent transactions to make money for Blizzard. That's related to things like identifying cheating, where it's not actually credit card fraud, but it's still playing the game in ways that we don't want people to play. So we'd like to be able to identify that and let humans go through those cases in detail to identify, was this in fact bad behavior? We talked about segmenting player types. That's sort of a mix of either of these and is involved heavily in infrastructure. Causal modeling of behavior is a big area because most of our games we don't really A/B test very much. So we like to be able to use the best models we can to understand as close to causality as we can get based on the data we have. We do some testing, and so of course data science is heavily involved in that as well. So I more or less have covered these topics. My contact info is there as well in case we don't get any questions you have. But with that, that's the materials.
So Alex can see. So if people have questions, they can raise hand, and we can try to.
How do I turn off screen share?
There should be a button on the top left or the fourth. Yeah. Hey.
Right.
Okay. Hey, do we have any questions? Any questions for Alex? One right over here on the right. Hopefully he can just hear you. I'm just going to do this. I'm going to be like a Muppet.
All right.
There we go.
Okay, so thanks for the talk. Two questions related. One is, do you actually find some that meta is kind of a dangerous, mostly from the input for the players first, and you as a data science just check, is it really dangerous, or was it ever the other way around? Like players are not complaining, but you see in the data something is not right, and we want to do something, before players starting to do.
That's a great question. The reason I had that pie chart of like data, intuition, and players was because all of those inform our choices, and at different times, one or the other will be the one that actually initiates that change. So certainly players will complain about things. There's two sides to that. Players will complain about things even when there is no problem. They just don't like the way things are. So that's that problem of like, you can only have a 50-50 win rate on balance with a closed population. So they can't have the win rate they want. So they may complain about things they don't like there. Relatedly, designers will often be the ones to initiate something. So they may feel that a deck has a really low win rate and it's really fun. So maybe we should be doing something to rebalance the game to make that deck more powerful because it's so much fun to play. And vice versa, nobody may be complaining that, Jade Druids or Aggro Druids are really good, but the designers don't like the state of the world where there's only 3 or 4 decks that are really viable at the high end of the skill tree. In terms of data, yes, we've had times where we've identified decks that either were overpowered or underpowered that then sort of got bubbled up to the designers for them to go investigate and say, is this a problem or not? My favorite case of that was the Dragon Warrior. So if you've played Hearthstone, Dragon Warriors are a really popular deck at one point in time and very powerful. What had happened was in the meta report, I had seen that they were a tiny, tiny, tiny sliver of the population with very high win rates. So I told all the best players in my department, because I'm terrible at Hearthstone, to go try it out. They all played over the weekend. They came back to me and told you, you're full of it. This deck is terrible. It doesn't work at all. Fast forward a month or so later, that is an increasingly large slice of the pie, and eventually we made some changes to help rebalance it.
I'm sorry I played Legends. But related stuff. Okay, can you actually go one step higher? I mean, if you discover some problems with meta, you have nerfs and stuff like that. So the meta will be shifted, and how well, given your data, you can predict, like, we nerf this card, so all of these decks will get lower and stuff like that. How good you are with this?
So we don't really have enough data to do that, and this is one of those weird things. It sounds bizarre that you can have all these players playing the game and still not be able to do very much. The reason is, in reality, that is a small data problem. And this is actually the same problem we hit in many of our games in terms of balance, where people from the community often think, well, you have all these players, you should be able to easily predict how any change you make happens. The problem is we tend to make many changes at once, and your data set is not the number of players, your data set is the number of changes. So given that we've only changed it, maybe we apply some hot fixes, but actual meaningful changes to the cards, like maybe once or twice an expansion, our data set is actually just maybe 3 times the number of expansions. Now we're talking on the order of dozens of data points. And at the same time, the changes they make to the game, the thing that makes Hearthstone such an interesting case as an example of this is it's basically adversarial with data science, right? What we want is the game that is the most similar in most ways possible. And their goal is every expansion introduce the most insane, most new, most different thing possible. So at best, our crap shot would be maybe we can kind of sort of fit something going on within expansions, but then our data set is now literally 2 or 3 data points. So we've often tried to do the exercise, but beyond literally just charting where things were and comparing against that, it's really hard to predict the outcomes of any changes based purely on data.
All right, time for like one more question, maybe.
So you're using this in order to do some amount of balancing, which involves, you said, adding cards that are in existence or taking cards away and putting them to the side. Have any new cards been just created in order to solve a problem in the meta based on this data?
That's a good question. I am not the one who's been doing it, so I could not give you the explicit example. But there's at least been major changes made, usually because the designers, when introducing a card set, are trying to make the card set around a theme. It's relatively rare that there would be building more than maybe some changes to the stats of a card based on what they've seen. The challenge being, if you're going to build a thematic set, it should feel different. If that card is already there, it's more typical that they will take that card and buff or nerf it to try and adjust its prominence to adjust the meta than they will to actually, like, they get rid of all dragons from a card set because the meta shows dragon warriors are strong. Like, it's an issue of impact versus scale of solution. So it is a great question.
I know, like in Magic the Gathering, they don't have the ability to just turn off a card by changing a flag and a piece of programming. They have to, ban it from the series, or they have to release a brand new card deck. So I guess you got a bit easier than them because you don't have to worry about the next printing.
Yeah, again, because Blizzard really cares about our community, we are somewhat handcuffed there anyway. Because while the code change would be really easy, nobody likes seeing their card removed from the game. We can't directly remove it, so then it's like nerfing it, but we don't want to nerf it too much because then everyone feels bad. It's like the general design philosophy when you talk to the designers is it's better to instead buff some other cards and make something else fun to play that's accessible than it is to actually weaken something. And then when we have the set rotations, that's kind of our mechanic for removing them out. So that's cribbed from the sort of Magic playbook sort of approach of just, we'll just let this card not be so powerful it's in most really good decks. And then eventually it'll just slip off the radar and we can actually fix the core problem with that as we introduce new card sets.
All right, let's thank our speaker one more time. All right, thanks, Alex.
Peace.
Yeah, I use them.
Yeah, let's make sure you can you present. That's important.
Okay, looks like we're good.
Put it on HDMI?
Yes.
Yeah, great. So this shows up. That looks pretty good. You can probably give people a couple more minutes. We're gonna have extra time at the end anyway. Yeah. No, we have closing marks that are scheduled for having 15 minutes, and they're not going to take 15 minutes.
I like it. It's kind of back to your
I'll just say, leave it to it. Well, I don't think it's not really relevant. No, I'm not going to tell you. The stickers are small.
I mean, the way it's going to work is that as soon as you start, there's going to be 4 or 5 people.
Yeah. So
come in.
It was unfriendly. They did the service was fine. It was just overpriced. My teacher discovered for being such an expensive restaurant, we should have better.
Their kitchen was packed up. So thank you very much. We're going to resume with our final session of the day. And take it away.
hi, my name is Henry Benetti. I am a senior undergrad at Pomona College, and I'm going to talk today about a project that I started as my senior thesis in mathematics. And I'm curious to hear what you all think and about feedback on future directions. It's called Clustering Player Strategies for Variable Length Game Logs in Dominion. So to start out, I'm going to introduce the game Dominion. It's actually a familiar game to the Games AI community. It's been studied before. And how the game works is you start with a small deck of 10 low-quality cards. And on your turn, you draw from your deck, and you use the cards in hand to try to gain new cards. The cards you gain and the ones you use get cycled back into your deck. So you're building an increasingly large deck. And cards have different costs, making some of them more expensive and harder to get than others, and making it smart to gain different cards at different times. Now, your ultimate goal is to get a deck that is dense in high-quality cards. There are 2 real ways that cards can be high quality. One is that they can be powerful and allow you to execute actions. So later, when you draw this card in your deck, as you cycle through, it allows you to do really big things. Like it allows you to gain more cards really easily. The other way a card can be good is in just let you win the game. It's going to be worth points, and at the end of the game, the person with the more points wins. And so it's what's called an engine building game, in which there's sort of two phases. In the beginning, you're trying to gain cards that allow you to execute actions. And it's also called building an engine in the metaphor of an engine building game. And then in the second phase, you're trying to use this engine you've built to just win, to execute a plan you've built and win the game. And when that shift happens is actually a big point of interest within the AI study of Dominion. The other thing that makes the game so interesting is that you're buying cards from a common pool. That common pool on top of these base cards on the top consists of 10 cards. Now, between the base game of Dominion and all of the expansions, there are 330 cards, of which you choose 10 to be in any given game. So every time you play the game Dominion, the rules are different, the set of actions you can take are different, the set of things you can gain are different. And these cards can get sort of arbitrarily complex, or there isn't really any streamlined way that they behave. They can range from draw cards into your hand so you can use more cards on this turn, or gain more cards to your deck from this common pool. And so some properties of this game that make it interesting from an AI perspective, it's partially observable and stochastic, making it, because it involves drawing cards from a deck and shuffling decks back together, making it difficult to build AIs for. It can be more than 2 players. It can be anywhere from 2 to 4 players. And unlike, say, chess, where there's 2 possible starting states, there's, because you choose 10 out of 300 cards to be in any game, there are about 10 to the 18 possible starting states for a game. And so my research question is, can we talk about how people play the game Dominion? Can we talk about the different, a term I'll define in a little bit, personas that people assume when they play the game? And due to the combinatorial explosion of the state space and even the starting state space, this certainly can't be described in a decision tree. But at the same time, that's what makes it so exciting from an AI perspective. If we can take how someone behaves under one set of rules and make a statement about how we believe they will behave under a different set of rules, that's a really interesting open AI question. And so I'm going to provide a little bit of related work. A lot of this work was spearheaded by Homegord in the past 5 years, et al. In the last 5 years, about a game of their creation called Mini Dungeons. And so they introduced this idea of procedural personas. The concept is that playtesting is really expensive and difficult to coordinate. And so if you could create AIs that would play the game according to different types of players, then you could automate the entire playtesting system. And so they defined a procedural persona, these AIs, as representing archetypical decision-making styles. And they applied it to this game of their creation, Mini Dungeons, in which, like a classic dungeon crawling game, in which a persona might be something like speedrunner, someone who just wants to finish the game as quickly as possible, monster killer, who really wants to fight all the bad guys, or meticulous, wants to check every corner in a methodical manner. And they showed that you can take these intuitive ideas, use them to create utility functions, and augment Monte Carlo tree search, which was introduced earlier today, in order to create such AIs. And this is a really great line of work when you have that starting spot, when you have intuitive, archetypical decision-making styles. So in 2011, Dr. Gold applied this line of work to Dominion, the game I'm talking about today. And he used clustering methods, clustering also having been introduced earlier today, to talk about, to try to divide players into different categories. And so he used a Bayesian method and started with seeds of classifying players into, the first category is roughly players who like flashy plays, who like, and the second category was players who like quirky or unique strategies. And the third category was players who like sort of using their own game-specific knowledge to outplay opponents. And these all seem somewhat intuitive, reasons why someone might, ways someone might play the game, if not totally discrete. It feels that many of these would actually really overlap. And what he found was that when you run clustering, when you run Bayesian clustering, about 80% of players merge together into one big cluster. And that the ending clusters don't match the original Cs. And so he warned against that players might not fit neatly into researchers' preconceived categories. And in a survey results, he talked about players talking about their interest in the game cross-cutting these three categories. And so Holmgaard et al. Showed that you can take these intuitive desires or personas and create AIs that produce human-like play traces, which I'm going to refer to now on as strategies. A strategy being how a persona plays out in an individual run-through of a game. And my research question is, can we take it the other way? Can we take play traces and make some statements about why someone might be playing the way they do, where their decisions are coming from? And so in a similar line of work to Dr. Brown earlier today, what I'm looking for is inherently intuitive and subjective and meaningful as opposed to totally quantitative. I'm trying to come up with something that feels right as this is why someone is playing this style. And so clustering seems like a natural choice. If you have access to a lot of different play traces, a lot of different examples of people playing the game, then you can cluster into different strategies. Now, again, I'm going to emphasize the difference between strategy and persona. Strategy can be, in this particular game, the player moved very quickly from start to finish. A persona is a player is inclined to do that across many playthroughs of the game. And so an important first step would be to try to identify these strategies. But in order to do that, we need feature encodings where the quantitative variance between points represents qualitative differences in gameplay. Now, this might seem sort of obvious or not even worth thought, but it's sort of the sticking point, because other researchers have found that similarity metrics, if you try to find ways to quantify play traces, a lot of similarity metrics are dominated by game length. So if you ask what game is similar to this game of Dominion that was 10 turns, you get another game that was 10 turns. Now, specifically in the context of Dominion, that's not something we want, because the largest predictor of game length is the number of players in the game. And qualitatively, it feels that the similarity between games, especially because it's less interactive than a lot of other games, it feels that 4-player games should not be considered similar to all other 4-player games just because of that. And so centroid clustering, or doing some sort of clustering method, will always give us answers. We'll always form clusters, and we'll always be able to look at the centers. But how do we know they're good? How do we know what differs between the clusters? How do we know that the similarity metric we've defined says anything meaningful? And so before I even do clustering, in order to sanity check the encoding, it would be ideal if we could create visualizations of the gameplay landscape to learn about what points are considered similar to each other. And so in order to do that, I use a method called tsne. So tsne is a manifold learning technique, which takes high-dimensional plots of data and tries to embed them in a 2-dimensional plot such that points that are nearby each other in high dimensions remain nearby each other in the lower dimensional mapping. You can see, in this case, it's the bottom right image. It's taking a 3-dimensional sort of S shape, and it's outputting this image in the bottom right. It does so by creating a probability distribution of each point naming each other point as its nearby neighbor. And sort of the key point here is that it's an asymmetric cost function. It much more heavily penalizes taking nearby points in the original high-dimensional feature space and plotting them far away from each other in the embedding than it penalizes far-away points in feature space being sort of accidentally sent close to each other. You obviously can't fidelidously represent all point clouds in 2 dimensions, and so if something's going to give, that is. And so I used data from a website called Dominion Isotropic. It hosted online plays of the game Dominion over 3 years, a total of 11 million game logs. And so to start out, I looked at one specific card set, one of those 10 to the 18 possible starting states. It was the most popular one, and it was still only used in 3,000 games of those 11 million, which speaks to this sort of the massive starting space. And all of the logs begin in text format, or existed in text format, needed to be parsed. So I'm going to spare you guys a little bit of the time about unsuccessful feature encodings, which I talked about in the paper, and skip to the one that was successful. And so if you encode a game not as a sequence of actions, but as a sequence of game states, and also normalize, then you can escape some of these problems I talked about, some of these problems other researchers have observed of a similarity being defined by game length. So in this case, because I'm using one card set, on each turn, for each card, I encoded the proportion of your deck that was that card. And so this vector, which represents your movement throughout the entire game, represents sort of the building of your deck in terms of proportions. And what you see in this image is that, again, this image represents nearby points are considered similar to each other by that feature encoding. And what you see is that there's good mixing. Similarity doesn't appear to be defined by game length. And so the question is, what is it defined by? And the answer is different card combinations. Different card combinations each occupy regions of this image. So I'll show you a couple. In figure 2, color represents the portion of your deck that is silvers and golds, two similar popular cards. And what you see, in figure 3, you see color encodes the proportion of your deck that is villages by the time the game ends. And so what you see is that there's a portion of this embedding that is dedicated to players who go all out for silvers and golds, and that there's a portion that's players who go all out for villages. And you actually even gain a little bit more information than that. You see that they exist on opposite ends of the embedding and that there's a gradient between them. This matches the intuition of people who know Dominion well, that villages synergizes really well with basically every card but silvers and golds. It works really well with any action cards. And so it would make sense that these would be sort of completely opposite ends of the spectrum. And so what's nice about this visualization is that you can query it for sort of arbitrary information. So what if you talk about starting moves? Now we're looking at proportions of cards in the deck just after 2 turns. So if in the first 2 turns you buy a silver and you buy a smithy, 2 cards in the game, yellow encodes the points that bought both of those in the first 2 turns. And what you see is that those points are really close to each other, indicating that people who started with these 2 moves went on to perform very similar strategies to each other. They're very similar in feature space. And that also matches intuition, that players who are doing that are going for the very specific, what's called a big money strategy. And in figure 5, you see that players who start with villages and smithies, another pair of cards, go on to do a lot of different things. Those points aren't necessarily close to each other, which also matches intuition. And now the thing is, I've said many times, I've talked about matching intuition, about matching expectations. And so what is perhaps clear at this point is that these visualizations haven't necessarily given me much new information. And the reason for that is that this was a clustering ran just on the most popular card set. And the sense of what cards work well together and what cards to use together is really well established for just this base card set. And so this allowed me to sanity check the clustering, that similarity, that points location in this feature space is defined by a subjective sense about what card combinations go together. But I haven't gained too much new yet. And so now the question, the real question is, how can we change this to compare games with different card sets? And this sort of goes back to my original research question. If you look at 2 people playing different games of Dominion, how do you talk about similarity or difference? If you say this player bought villages and this player doesn't, that's kind of meaningless if the second player didn't have the option to buy villages, because again, the important fact is that the options available to each player are different game to game. And so what I chose to do was you only encode the cost of the card. Now cards cost basically between almost all cards cost between $2 and $6 dollars or treasure. And so you lose a lot of information by only encoding the cost of the card. And instead of asking what proportion of your deck is, say, village on turn 10, you ask what proportion of your deck cost 3. And so really in pace. If you ask yourself how 2 different points in this feature representation can look different from each other, one might be that one player chooses to buy cheap cards for a long time and then at the very end really picks up the pace, whereas another player is buying it much quicker but sort of accelerates quickly and then plateaus. And so in the language, this really ties back to the language I started with about engine building, that some players might take longer to build an engine, but it is better and moves quicker than another player who might very quickly start executing, but it's not as good. And so what I did was now, instead of just using that one card set of 10 cards, I looked at the 30 cards available in the base game, and any subset of those 30 cards I examined. And so it went from about 3,000 points in the previous image to 9,000 points in this one, and including just as cost. What we actually see is that these yellow points again denote the silversmithy start that was a couple images ago. And what you see is that these points are actually pretty cohesive. And there's a lot of different visualizations that back this up, and I've sort of spared you guys the dozens that I made. But this is interesting because the silversmithy start, the feature embedding doesn't know what a silver is or what a smithy is. And in fact, this looks identical to any other possible start. And so really what that shows is that this start is indicative of a unique game pace. Players who start with this are going to go through the game moving at a pace unique to them. And also looking at villages again. This is similar to the gradient of villages I showed a few slides ago. The gradient of villages you have in your deck corresponds to a gradient of pace. And so really what I'm arguing and what I'm seeing is that the distinct clusters in the limited card set visualization remain distinct when pace is the only thing clustered on. That means that a lot of this information about what strategy you're using can be encapsulated in this sort of parametric definition of cost, which would allow you to compare across card sets. And so I'm proposing pace as a somewhat intuitive definition of different strategies, different play traces of Dominion. This matches my anecdotal evidence of Dominion as a game where oftentimes it ends and one player would say, oh, if the game had gone 3 more turns, I would have won. This is really important. This is a really interesting point in the context of engine building games in general. The idea of pace is something that's somewhat well studied about when do you make this turn into buying expensive cards, when do you make this turn into the end game. And so what I'm exploring right now and the sort of future directions and what I'm looking for input on is that I've argued that it's a defining characteristic of a strategy. If you look at a trace, you can sort of encode it, you can sort of give it this finitely or the small dimensional value of pace. But does it define a persona? Does an individual player have a tendency to always be patient or to always be quick? That's a lot harder to get data and a lot harder to get kind of consistent data for individual players. And so that's something I'm working on right now. And so the other thing is I'm working on even larger card sets. Since putting this together, I've seen that it works as you expand well beyond that 9,000 and look at even more card sets. And trying to define it actually as according to an equation. Can you define patience versus speed according to like a numeric real value? And other things I'm looking into is how do certain card sets favor patience versus speed? Are there card sets that make this dichotomy stronger or weaker? And taking a step back, what games are this true for? I've thought about a lot of engine building games. Those of you who might be familiar with Civilization might realize that under different iterations of the game, sort of so many rules change between Civ 3 or 4 or 5. And yet your play style can still be categorized by a few things like someone might say you're very warlike or you're not. Or another thing is this idea of pace. You are very patient. You turtle for a long time and then execute your engine later versus you're very quick to get into the action. Thank you.
Well, if maybe the next speaker could get set up during the Q&A.
Any questions? Yes.
Yeah, so there's a lot of interpreting of the TC plots. Can you say a little bit how you chose the perplexity parameter used in TC? Because that changes so much the structure of what you see in these pictures.
So that is, well, so TC is actually, it argues and it somewhat claims that it's somewhat robust to perplexity. It is actually robust, that it shouldn't dramatically alter the plots that it produces. Specifically, for that first plot, I ran it on a few different perplexities and found that the sort of groupings remained the same. If not, everything just was sort of shifted around. And so in my experience, I found that it didn't have a huge effect. All right, thank you.
Hi, I'm Eric Piet. I'm a postdoc researcher from the Maastricht University. I'm here to talk to you about our last paper, Strategic Features for General Games. This paper is done by Cameron Bourne, Johnny Summers, and myself. This is mainly the work of Donny Summers. This is a part of his thesis, but it was not possible for him to come. This work is a part of a digital Ludem project. This is a 5 years research project. It's recently launched at the DKL, so the Department of Data Science, Technology, Engineering in the Maastricht University, and it's possible thanks to the European Research Council. The main goal of this project is to realize a computational study of the world's traditional strategic games throughout record human history. So on this project, we have 4 main objectives. The first one is to model the full range of traditional strategy games is only one single playable digital database. And for each of these games, we want to play them at a competent human level. So we don't think about working on a super human artificial intelligence like AlphaGo, but just at a competent human level for all the games. Unfortunately, for a lot of ancient games, we don't have all the rules, or sometimes some parts of the rules, sometimes some different possibility for the rules. So we have also to evaluate the different rule set reconstruction for an historical or authenticity and quality of play. And sometimes we have to improve this rule set where it's needed. So to sum up, the goal is to improve our understanding of traditional games using modern AI techniques, or like we said, using modern techniques on ancient games. On this project, we provide a new kind of general game playing platform called Ludi. This is a Ludem-based system. A Ludem is a game named the needs of game-related information. For example, here you have the Ludem modulation for the tic-tac-toe game. We have different kinds of Ludem to define this game. The first one is to define the different players, so here white and black. The second one is to define different kind of equipment on the game. For the game, we just need a square board, tiling by square or 3 by 3. And for the rules, we have 3 kinds of rules: the starting rules, the playing rules, and the ending rules. Of course, for tic-tac-toe, we don't need starting rules because at the beginning the game is empty. But we have 1 playing rules. At each turn, the player can add one of his own pieces on an empty place on the board, and an ending rules. If the player realizes lien of 3 of his own pieces. Thanks to this modulation, it's possible to encapsulate the key concept of the game. And because we think the game like DNA, whereas the Ludem are building blocks. So with this kind of thing, it's possible to identify easily the similar game if the different game use some different similar Ludem. And thanks to that, if we provide some different great features for one game, it's likely probably to apply the same features for some similar games. So the goal of this paper is to learn strategic features for a big range of games. Because of Ludi may need able to model 1,000 most influenced traditional games throughout history, and for each of them to learn and to play and evaluate up something like 1 million candidate rule sets. Through the self-play learning of simple lightweight features and embodied strategic knowledge about the game being modeled. The core method for the Ludi system for AI move planning is MCTS, but to apply only MCTS for all of this game, we cannot get a Neumann competent level for all of them using just MCTS or different algorithms using these technicals. So we want to improve MCTS by different possibilities, and one of them is to bias the player out thanks to domain relevant features. An example, exists a lot of different previous work on different games to improve MCTS thanks to the features. Here you have the game of X. This is a very famous game. At each turn, a player can put one of his own pieces of its square, and the goal is just to create a link between the two opposite sides of the board, connection, like here, where the blue player wins. And of this game, of course, it's possible to apply MCTS, but if we just add one features, we can improve really efficiency CTS. Here you have the most famous one features for the game of X. If the last move of the black player was to play A between two white pieces, we encourage the white player at the next turn to play A to get a connection between his pieces. Just in adding these features to MCTS, we get 35% winnings against the normal MCTS. So, like we can see, is just in adding some simple features, we can get really more efficiency with MCTS. And so our goal is to learn this kind of features directly by self-play. And the features have to be modeled in order to be geometry independent, to transfer the different kind of features from one game to another one, with different kind of geometry for each of the game. So the features indicate strategic potential for MCTS. For us, we define features like that for our range of game. Our features is defined by a pattern specifying elements that must be present or absent in certain location in game state, where the features are to work. And an action, encourage or discourage to play if features false. A pattern consists of a set of elements described by the relative location on the graph, and the relative location of each element is defined by a work. Thanks to a sequence of adjacent steps. Like you can see here, we define the different works thanks to different floats. For example, for a square, if we play to a value of 0, we go to the north. For a value of 1 or 4, we go to the east, and for the opposite value to the west. And we do the same thing for the different kind of different tile for one game. And so we can get this kind of works 0, 0, 1, and 4 to model a knight move on a chessboard. And it's possible to apply the same knight move to any kind of board. For example, here you have the Gaia board, is a board with different kind of tile on it, some X, some triangle, some square. And if we apply the same kind of knight move on it, we get this kind of move for the knight. So as you can see, this is the same thing for the beginning of the move, but for the last one, this is the X tile. If you look here, we have 1 on 6 and 1 on 3. So for 1 on 4, it's just a value between the 1 on 6 and 1 on 4. So the two moves are possible. We just have to apply a probability of 50% for each of them. And we identify two kinds of patterns, the local one and the global one. The local one is an absolute filter pattern. It's applied only to some specific location. For example, for chess, we apply only some patterns of function of the knight position. And some kind of other pattern can be applied relatively to any kind of position across the board. For example, for the game of X, where the pieces are anywhere on the board, we can apply this kind of thing. Thanks to that, we identify two kinds of features. The first one is the reactive features. These features using the last move of the player. For example, this is the same features I explained before. If the last player plays here, we encourage the next player to play here. If you detect this kind of features on a board, we can generate bias features to apply it to any kind of geometry. For example, here in a square board. And for other kind of board, other kind of features, the proactive features, it don't depend on the last move of the next player, but only for any kind of current pieces of the board. For example, again for the game of X, if the white player has the pieces at this position, we encourage him to play at this position to get a connection later. and we can generalize that to this kind of base features to get something for any kind of board. So thanks to that, it's possible to associate all the features to get directly any kind of features in any kind of position, including rotation and reflection. For example, for this kind of base features, if you actually including all rotation and reflection of an X board, we get directly from that any kind of other features for any position on the board. We just have to check if the home position is on the board. For the feature generation, many ways are possible. If you look on the previous work, all the features use expert knowledge or extracting them through supervised learning from human expert. But for us, it's not something suitable because we have a really huge range of games, 1,000 games. Between them, that's really, really different. For example, we are interested about all the games before the 20th century, and we have some card games, some starting games, some games like chess, some Xbox. So it's not possible to apply all the knowledge for each of the different games. And a lot of them are really, really old. Some Egyptian game, for example, currently no human plays the game, so we don't have any kind of information of that. So it's not possible for us to using some human knowledge. So we want to learn everything directly from artificial intelligence, MCTs. And so for that, one advantage of our description by the algorithm is possible to reusing the similarity between two games. For example, for the game of X or the game of Go, for each of them, we have to define a scalar game. The player have to play at any empty position. So we have a rhythm called 2 for any empty position. And so we allow only the features which can be applied to this kind of game and not the other one. So the number of different features are really less important. And of course, we have to think about the consuming time to evaluate the different set of features on the compared to normal MCTS. But after some relative stakes against some MCTS, the time using for evaluating the set features is something really not important compared to the time using for the simulation. So it seems to be good for us. And thanks to the features, it's possible to define some different kind of simple strategy thanks to a set of features. For example, in some game to win, it's important to create some group of 3. It's possible thanks to this kind of features. For example, if you have only one pieces, one quad, the other player to play anywhere around it. But if you have a group of 3, we discourage it to play anywhere around. So the player is oriented to create some group of 3. Something for some other kind of strategy. For a game like Yavalta, the goal is to create a line of 4 and not a line of 3, because if you create a line of 3, you lose, and if you create a line of 4, you win. We can model this kind of thing with a set of features, with 3 pieces like this, we encourage to play there, and for 2 pieces, we discourage to play there, or something to create a line and not a group for this kind of the last set of features. One great benefit with our rhythm modelization and to transfer any kind of candidate feature for any other kind of similar game. Because thanks to the modelization, we can identify if 2 games use the same kind of rhythm between them. And so for each kind of rhythm, we apply some different kind of pattern, and we can reuse directly the same knowledge between 2 games similar. In Lodi, each rhythm corresponds to a Java class with an appropriate name. So one other idea is to directly, thanks to this name corresponding to a Java class, it's possible to use directly English caption to get the features not with something in logic pronunciation, but directly in English. For example, make a line of 4 can be directly extract for the description of the game to get the features. So at least the work in progress. This project is something really young. If you are interested about it, you can go to this link, ludem.eu. Thanks for your listening. And for the question.
Do you observe a transfer of these features across different games, or is that like a feature that you can use to make other predictions about the design of these games whose design is partially unknown?
Yeah. We detect some different kind of features for some different games after for our current experiment, something like 300 self-play. And after that, it's possible to get these features to some other games similar, thanks to that. And sometimes so there is some really old game, we identify some new kind of features can be also really interesting for some parts of a game and not for all the game.
And just for a sense of generality, Ludi, is it for like symmetric 2-player or like K-player territory control games, or does it?
In theory, we can model any kind of game, possibly model in Java.
Mm-hmm.
So this is a the system is currently in progress, so we update it currently because it's really young. But we can model any kind of board game, any kind of card game, 2 players, 1 player, plus of 2. For the moment, we limit to 8 players because we can update it because for now this is our limit. So yes, the range is really huge. It's in theory it's also possible to add some real-cheese game, but this is not our goal because for some motion games before the 20th century, of course.
What does the feature learning look like for like a card game, for example?
For now, we are only interested in the transferable game for the first 2 things. So I think maybe it's a little hard to get directly a graph to explain the features, but thanks to the English caption for each kind of game, we can explain it directly. For example, to play the card, the highest card at this moment, that kind of thing.
Okay. Any other questions? Thank you very much.
Hi. Okay. Hi, I'm Alex Braylon, and my co-author, Risto Nikolainen, is right over there. We're from University of Texas at Austin, and I'll talk about discretization of the game space by environment variable attributes. Let's see if this works. Oh, yeah, it worked.
Yeah.
All right. So I don't know if I really like this mic, actually. I'm not going to do the mic thing. This is a small room, right? So here's the problem we're dealing with. We have increasingly complicated games. In particular, we were working on a massive multiplayer shooting RPG game. So it's pretty complicated. A lot of the aspects of the game are either not explicitly coded in the game, or the data for it is not really recorded. So we have to, we want to be able to learn some things about the game automatically, right? And because they're so complex, we want high-level abstract features to be learned. And there are many use cases for this kind of ability. Either we want to build bots or create non-player characters that behave somewhat intelligently, or we want to produce analytics for the players and for the designers of the game. The focus on this is going to be on the geospatial environment. We want to build a kind of feature or feature space or module, if you want to think of it that way, that can represent what is predictable from the locations within the game in XY space. So I'm going to use the term geospatial just because if I talk about space, you might think parameter space. So I want to be clear. When I say geospatial, it means Cartesian coordinates, X, Y. This particular game is, it's a 3D game, but the space is 2D. So we use X, Y. Just a little bit of background. I don't want to name drop everybody, but this problem of trying to learn things from very complex games that aren't explicitly encoded in there. There's been work at the previous workshop last year. I didn't attend, but I read the prior work. There's stuff like, learning a graph structure of interaction between agents and objects, learning the idea of interaction modes, either out of all the possible actions that you can take, what are the subsets that are actually reasonable to take in any particular situation. Hierarchies of concepts over here. So this is stuff that's not explicitly coded by the designer necessarily, or at least given out. So it's useful to be able to learn it. There are others that I'm not going to call out, but there are others. So what is special about this geospatial modeling that we're looking at here? Compared to some of the other things, there are a few differences. So one is the input. What you want to do is you want to predict things from this very kind of simple input, which is your XY location. It's simple, but unlike a lot of other inputs you might deal with in machine learning, well, I don't want to say in machine learning generally, but unlike a lot of the other game inputs, the variables are continuous, both in the sense that they're not discrete, they're in the real number range, and in a kind of temporal sense that you're constantly observing where your XY location is, rather than seeing it rarely. And also importantly, the kinds of things that you're trying to predict from this input can be very complex. You could be trying to predict everything. What kind of objects you might find, what kind of enemies, creatures you'll run into, where are the vendors, the quest givers, the exits, the death traps, all kinds of things. So like here's an example map from the game that we were dealing with. And this doesn't even list all the enemy types, which there could be hundreds of enemy types and enemies just all over the board. So in contrast to this input, the output is generally like a discrete number and not constantly encountered. So for example, encountering a boss is rare. So different types of bosses. So that's what makes us different. So one question to ask is, so what's the point of this and how do we measure the effectiveness of it? So just to reiterate, we're trying to predict all these various things about the game from the XY coordinates. How do we produce something that's good? Well, we want to look at how useful it is. So by usefulness, I mean the predictive power. If I'm predicting something, I want it to be accurate. I want it to make mistakes. Optionally, the interpretability is important. I'd say more often than not, it's important. And then there's other categories, efficiency. So, you don't want to take up too much space in memory just to store all this geospatial model, and you want it to be tractable to compute. So, for instance, with the predictive power, you might measure the cross entropy loss for a categorical outcome. So you're trying to predict at this space that my agent is sitting at here, what's the probability of encountering a wolf, the probability of encountering a sheep, a turtle, a treasure chest, a boss, all the things that you might encounter, there's a probability, and you can measure the accuracy by using cross entropy measure. Interpretability is more qualitative, but we like to think, why it might be important is that you might want your NPC to be able to communicate to a player in a way that that makes sense to the player. So of when you think of the types of outputs that might be produced by various models, you can think of kind of a kernel family where you're saying, okay, I'm right here at these coordinates, and I saw, this is what I saw on all these other coordinates nearby, and based on interpolating from all those observations, the chance of finding a wolf is X, which is kind of hard to communicate compared to something like, I am in this type of biome, or this kind of area 7, for example, where this is the probability of finding a wolf is 0.12. So that's the seemingly more interpretable kind of output. For efficiency, we look at memory requirement is going to be basically, well, I'll talk about it more in the next slide, but it's just, how complex do you want this this prediction space to be? I'll get into it a little bit more. Compute time is, we're not really going to talk about it that much, so I'll kind of skip over. But it's kind of self-explanatory. So the kind of approach that we take here is to produce this concept of biomes, which are discrete areas that are demarcated by some boundaries. And there's a limited number of these biomes. And what you do is for any XY coordinate in the map, it belongs to some biome. So this is Earth, and there are different biomes in here. These are not learned automatically. This is just from the internet. And the idea is each biome, you're going to learn not only what are the boundaries of that biome, but then what is the probability of encountering every type of object in each biome. So in this paradigm, you can measure the memory efficiency by the total number of biomes and by the simplicity of the boundary definitions. I'll show a better picture in a little bit, but basically, if you want them to not overlap too much, well, I'll show you in a second. But one way to measure that is to look at for every observation, you say, okay, every point in space, in other words, what are the other observations nearby, and do they belong to the same biome or do they belong to a different biome? And if you have too many points in space that are next to each other and all from different biomes, it's confusing and it's too costly to store. So here's an example of two techniques that you might try. So here we have a geospatial input XY, which is just two continuous numbers, and an observation attribute output Z, which is well, each observation is going to be a one-hot encoding of what you observed there. But there could be the length of that one-hot encoding is the number of types of objects. So if there are 400 different types of creatures that you might observe, that's a 400 length one-hot vector that's encoded by Z. So these are two baselines. So let's say you did k-means or some clustering algorithm on XY. So you're just clustering together all the observations that are nearby each other in the XY space. It doesn't matter what Z was, meaning it doesn't matter what you observed. So at each point here, sorry, it's kind of going fast. This is X, this is Y, this is a game map from this game, where each point is an observation. And if you just do k-means on XY, it doesn't really matter what you observe. It just kind of partitions it out into more or less equally spaced areas. On the other hand, if you do k-means on Z and you ignore the XY coordinates altogether, what you get is this overlap problem where, let's say, purple could be wolves. You see wolves everywhere, and then you see maybe red is turtles, and they're kind of mixing together, but there's not really a clear definition of what's one area versus another. Maybe you can see it more or less, but you need a way to quantitatively define these biome boundaries. So this is kind of insufficient. So the two alternatives that I tried, the idea is well, you want kind of the best of both worlds. To go back for a second, you want the clusters to be built in such a way that they are their entropy is optimized so that each one kind of stores the maximal predictive performance of finding each type of object. So you'd say like, okay, I want this one to be a cluster because there's a lot of red there, and I want this one to be a cluster because there's a lot of blue, and so on. But unlike this example here, you want each cluster to be kind of contiguous. You don't want them overlapping each other. So these are two examples, and I kind of named them for some reason. One just to have an abbreviation, GCC. The idea is to just run a normal clustering algorithm over Z, like in this example, but have a constraint on how you decide to add a point to the cluster. So this graphic here, if you have this cluster that you're building where you have a lot of wolves, you see a wolf over here, you want to add it to the cluster because this is kind of a very wolfy cluster, but you check the XY proximity, and if it's too far away, maybe you say, no, not yet. And if it's close enough, you'll say, okay, I'll add it. And then one alternative, GAC, is to do something similar to what's done in real life. If you see kind of maps that are divided by county or by state or by country, and you just do the statistics for each boundary, and then you're done. But here you don't have, in this game, you don't have the boundaries predefined for you. So you have to automatically just do it. So in this case, you just say for each observation, I'm going to have some radius that's pre-specified, and look at everything around you. So in this case, you have this W. Within the radius, there's a turtle. So I'm going to say 0.5 wolf, 0.5 turtle for this one. Same thing for this one. This one's a little far away, so its radius doesn't encompass anything else. So it's 100% wolf. And then once you've done that conversion from Z, which was the one hot encoding, to a continuous encoding like this, with Z hat, you just run this same algorithm, but on Z hat instead of Z. So what that looks like, these are those two, the results of those two. GCC will produce something like this, and GAC will produce something like this. So as you see, compared to these maps before, you get kind of what you want. So you wanted that to be, this blue area to be its own cluster. You get that kind of in both cases, and so on for the other areas that you want it to be a single contiguous area. The main difference between the two that you can observe is that in GCC, every biome has to be more or less contiguous with itself, whereas in the GAC, you sometimes see biomes that are kind of remote from each other. They don't have to always be contiguous. So we had some measures for evaluating the quality of such a discretization algorithm. Like I said, we ran this on a modern, massive multiplayer first-person shooter game. It's also an RPG. It's cooperative also, so maybe you might guess what it is. And there are there are actually several maps. I used a few of them for just doing all the development, and then held out 3 on which to run the experiments. So for those 3 maps, there were 5,000 to 18,000 observations done within this time period. I think it was a month. And there were 200 to 400 types of creatures. We only looked at creatures. We didn't look at like items. And the measures that we were looking at were this overlap condition. So how many of the same type of cluster, or how many observations within some nearby radius are of the same, are of a different biome. So the higher, the worse. Cross entropy, this is your predictive performance measure. And then just compute time in seconds, just to see. And so what we see is it's kind of intuitive. So we know that this k-means on x, y. That's where it doesn't take into account the object encounters at all. So oops. So it had the worst cross entropy, the worst predictive performance. K-means on Z, it's unusable because all the different points overlap each other. You don't really have discrete contiguous biomes. And then between these two, actually, the slightly surprising thing is that the better one was GCC. So just to recap, GAC is kind of like what we do in real life, where we have counties, we have boundaries, counties, states, or whatever, and then we aggregate the statistics for each territory, and then that's how we represent, that's how we produce the biomes, so to speak. And GCC is this kind of hierarchical approach where you're hierarchically building your cluster up with the constraint of having a certain proximity in the XY space, which I don't think people generally use. So it was kind of surprising that it did slightly better. I mean, not really significantly better, but slightly better. So the conclusion, we want to use geospatial information in our models. If we want to do something like player modeling, even something like matchmaking, as the other Alex spoke about before, if we want to infer this is actually how this came about in the first place, is we were trying to do a kind of matchmaking model for this company, and we would see what the players would die in certain places, they'd kill in certain places, but the areas that were defined by the game designers were so large that it was kind of, we wanted to know, we need to adjust our estimate of a person's skill based on the difficulty of the location that they're playing in, but we need a much more granular definition of location. So that's what kind of gave birth to this project, and we think it's important for other purposes more generally in player modeling and game modeling. They need to be predictive, interpretable, compact, and trackable. That's, I guess, kind of machine learning in general. But so this notion of the biome, I think, is useful. It's kind of in contrast to a more kind of like a smooth type of prediction surface where every type of object you might see, the probability changes smoothly, as is the case in some kind of geoscience application where you're trying to do oil discovery or resource discovery. You want an accurate prediction, but you don't really need it to be interpretable. This biome concept is a lot more interpretable and compact, so I think it's useful. These two methods, I think, are fine. There are probably better methods if we continue working on this, but it was kind of interesting to compare the two. It's not totally complete work, so there's still much more to do. We do want to integrate with larger models because some of these kind of these features that we're learning, if we're using them as predictors, they might be collinear with other features that we're looking at, and so we need to kind of learn big models together. We didn't even talk about actually going and then defining the boundaries around them. I think it would be straightforward, but I didn't really want to get into it. And there's things to do like once you have discrete biomes like this, you might see weird behavior at the edges between the two because of the way we're discretizing rather than using a smooth surface. So there are possible extra techniques to put on top to kind of interpolate when you're near edges between different biomes. And the more interesting thing is to look at if you had a game that was fully 3D, where it's not just 3D visuals, but traveling on a 2D surface, but actually fully 3D, like a game that takes place in space, for example. You can even include the dimension of time into your biome definitions and have a kind of like a seasonal biome. That would be cool. Thanks, reviewer, for recommending that. Yeah, so those are the future directions. I don't have a thank you slide, but thank you.
Do you have a sense of why GCC did slightly better than GAC? Was it the data or the game or something else?
It was actually a bit surprising. And so I ran it on several maps. And in the paper, you can see by map the performance. Actually, GAC was the one that a priori I would have thought would be better because it's a little bit flexible in how it defines the boundaries, and it's more kind of a default thing to do. So GAC did better in one map. So I did 3 big maps. GAC did slightly better in one map, and GCC did slightly better in 2 maps. I don't think it's really a significant finding. The compute time is a bit better for GCC, but that's because you have to calculate the neighborhoods. If you had predefined little areas, if the game gave that to you, then that would reduce the compute time for GAC. And the overlap, honestly, I'm surprised why the overlap is better for GCC too. I don't have a good explanation. Yeah.
Just for some context, what's an example of some like external validation for these kinds of clusters? You say it's like useful in some other like downstream prediction classification kinds of tasks. Are there some examples?
Yeah. So I started talking a little bit about. So what we were originally going to do was. So I'll give you 2 examples. So one is what I briefly mentioned. If you wanted to do something like matchmaking. So in this game, it's a cooperative shooting game. You go and you play with other people, but you want to have a kind of a balanced team to go in and play at difficulties that are appropriate for that team. So you need, well, first of all, you need some notion of how skilled the player is. In this case, in this example, actually, the data that the company gave us was big in terms of rows, but small in terms of columns. Like we didn't really know what was going on a lot of the time, so it was hard to infer how good a player was. We knew where they died, and we sometimes knew what they killed. But in order to infer how good they are based on where they died, you need to know how difficult, how important, or how difficult is it to die here given your skill level. So what does here mean? Because the maps provided by default by the game are gigantic. So we needed to kind of have a more granular feature space for that location. The other example was going to be something that the game designers wanted, was to automatically find places where that were causing problems for players. By that I mean there's maybe a bug in the game, or maybe something that's way harder than it's meant to be relative to things there. So it was kind of like an automatic way to find maybe places where people got stuck in the geometry, or people were doing some kind of exploit. But again, the same problem was we didn't really have a good notion of what is here. We know the XY coordinate, but that by itself as a continuous variable is kind of hard to do anything with.
When 3 is being released?
I thought it was already. No, it's not released yet. Sorry, I played 2, but I'll get started playing other games now.
Thanks very much. Well, I don't really have much to say. I just want to thank everybody for coming, for talking, for asking questions. Let's see if I can figure out how to get this thing over to the other thing. I want to extend another thanks to our reviewing committee and not zoom this out. And to my fellow co-chairs, especially Matthew Guzdow running the screen, and Samus Snodgrass and their tireless efforts to get papers out of people. If you
Squeeze them.
are, okay, I'm just going to show it over here. If you are interested in serving either on our reviewing committee or organizing committee next year, do get in touch with me. My email's here at the bottom. It's illegible, but I'll put a couple cards up.
It's also on the website.
It's also on the website. It's everywhere. And our proceedings are available in an archival state at CEUR, and that link will also be on the website. So thank you again for coming, and have a nice day, and have a nice rest of your conference.
Yeah.